Welcome to EDU World Space.
We know from the statement of this problem that a 2 meter length of wire is made by joining two pieces of metals together. One is a piece of silver of length LS of 120 times 10 to the minus 2 meters, and the other material is copper with a length LC, which is 80 times 10 to the minus 2 meters. And both of these metals have the same diameter of zero point 0.6 times 10 to the minus 3 meters. We're told that the wire is at room temperature so that we can use table 25.1 to find the resistivity. And we're told also that the potential difference of 9 volts is maintained across the wire. And we're asked to find in part A the current in the copper section of the wire. Well, this is like a circuit with two resistors in series, so the total current that's flowing in the circuit is the same for both resistors. And the way we find this is by using V is equal to IR, right? Where R is the total resistance. Let's call one RS, which corresponds to silver, and RC, which will correspond to copper. So we have V is equal to IRS plus RC. Okay. We know V, that's 9 volts. We don't know I, and we don't know RS and RC, but we have enough information to find the resistance. So we can use R is equal to resistivity length over cross-sectional area. So we can calculate each one of these RS and RC, and let's do that on the next page. So resistance for silver, the resistivity of silver times the length of the silver segment divided by its cross-sectional area. And if I put in these numbers, and I have 1.47 times 10 to the minus 8 ohm meters times 120 times 10 to the minus 2 meters over pi over 4 times 0.6 times 10 to the minus 3 meters squared. And I have this 1 over 4 here because the radius is 1/2 the diameter, and this is the diameter. So for this number, I have 0.062 ohms. And now we perform a similar thing to find the resistance of the copper segment. So the resistivity of copper, 1.72 times 10 to the minus 8 ohm times meters, a little bit higher, multiplied by the length of that segment divided by pi over 4. So we're told they have the same diameter, so they'll have the same cross-sectional area. And this number is 0.049 ohms. Okay, so now using V is equal to IRS plus RC means that I is equal to V over RS plus RC. And we know that V is 9 volts because that's the voltage that's maintained at the ends of the wire. And we just computed the resistance for the piece of silver and a piece of copper wire. So we just add them up. And this gives me a current of 81 amperes. Okay, and so the 81 amperes will be the current that flows through the segment of silver, but also in part B, they ask, or rather, in part A, it's for copper, and part B is the current in the silver. Well, it's the same as in part A, right? Because it's the same current through the each piece of wire because charge is conserved, so one piece won't have a different charge or current flowing through it than another piece. That's answer part C on the next page. So part C asks for the magnitude of the electric field in copper. Okay, so we can use that. There's this equation, I don't remember which number it is, but rho is equal to E over J. This is the resistivity is equal to the electric field, the magnitude of the electric field over the magnitude of the current density, or the electric field is equal to the resistivity times the current density. But we have that the current density itself is equal to the current over the area, and we have the resistivity is equal to the resistance times the cross-sectional area over the length. So if I substitute this expression for J, this expression for rho into here, so this one here, this one here, then I will have E is equal to RA over L times I over A. So we'll have I R over L, okay, which is V over L. So we'll use this part. Let's just use the segment over here. So the electric field in which segment? In copper. So in copper is equal to the current times the resistance of copper divided by the length of copper. So we found that it was 81 amperes times 0.049 ohms divided by 80 times 10 to the minus 2 meters. So this gives me 4.93 volts per meter. And I'd urge you to double check all the numbers. The formula here is correct, but just in case I've made a mistake in plugging in the numbers, it's good for you to double check for yourself. In a similar way, we can find the part D, which asks for the electric field in the silver part of the wire. So it has the same current. Sorry, it was a typo. So again, it's 81 amperes times the resistance in the silver part. Over here, I mistakenly wrote S where I meant C, but I think I plugged in the right value. 120 times 10 to the minus 2 meters, and this gives 4.21 volts per meter. Okay, and now we'll do part E. So part E asks for the potential difference between the ends of the silver section of the wire. So Vs is equal to I times Rs, which is equal to 81 amperes times 0.062 ohms, which is 5.06 volts.